It is 2:17 in the morning. Your pager goes off. Your e-commerce platform just went dark. Orders are failing. Payment timeouts are spiking across every region. Your monitoring dashboard looks like a Christmas tree. You open your Kubernetes cluster. 3 pods in the checkout service have OOM killed and are stuck in CrashLoopBackOff. Your database connection pool is exhausted because the crashed pods left open connections that were never properly released. And because those connections are not being cleaned up, your session management service is now queuing requests it cannot fulfill. The queue is growing faster than it is draining. You know exactly what to do. But diagnosing this cascade is going to take you 15 minutes minimum, then another 20 to roll back the deployment, flush the connection pool, and verify that the system has actually stabilized. 35 minutes of degraded service, at minimum. Now let me show you what happens when your cluster already knows how to fix itself. Same failure scenario, same OOM kill, same cascade beginning. The AI observability layer detects the memory anomaly 11 seconds after the first pod crashes. It correlates the memory growth trend with a recent deployment, identifies the probable root cause, and executes an autonomous rollback. Total resolution time, 54 seconds. 0 humans paged. 0 sleep interrupted. That is what this video is about. The scale problem human in the loop SRE cannot solve. I want to be direct with you about something before we go any further. Traditional site reliability engineering is genuinely excellent engineering. The practices Google codified in their SRE book, the error budget framework, the service level objective methodology, the runbook discipline, all of it is battle-tested and correct. I am not here to argue against any of that, but here is the specific problem that the traditional SRE model was never designed to handle. The average modern microservices platform at any meaningful scale runs hundreds of services. Each service has its own deployment cadence, its own resource profile, its own failure modes, and every new service you add creates new interaction surfaces with every existing service. 2 services create 1 interaction surface. 10 services create 45 potential interaction surfaces. 100 services create nearly 5,000. Netflix runs over 1,000 microservices in production. Amazon runs tens of thousands. Uber has hundreds of services in the ride dispatch domain alone, as we covered in the previous video. At that complexity, the math stops working for human-in-the-loop incident response. The average mean time to detect an incident in a complex microservices environment is between 8 and 14 minutes. The average mean time to diagnose root cause after detection is between 20 and 45 minutes. Mean time to remediate after that is another 15 to 30 minutes. For a platform processing $10 million in daily transactions, 60 minutes of degraded service is not an operational inconvenience. It is a 7-figure revenue event every single time. And the answer is not to hire more engineers. Hiring more engineers does not solve a problem that compounds faster than headcount can scale. The answer is to build a system that can observe, reason about, and act on its own health without waiting for a human to make the first decision. That is what AI-powered chaos engineering and self-healing Kubernetes infrastructure are fundamentally about. What AI-powered chaos engineering actually means, there is a lot of confusion in the industry about this, and I want to clear it up before we go deeper. Most engineers hear chaos engineering, and they picture Netflix Chaos Monkey, a tool that randomly terminates production instances to force the system to prove it can survive individual component failures. Chaos Monkey is genuinely important, and we will cover it in detail shortly. But chaos engineering and AI-powered self-healing are 2 distinct capabilities that work together. Understanding the difference is critical. Chaos engineering is the practice of deliberately injecting controlled failures into your system to expose weaknesses before they become production incidents. You are the attacker. Your system is the target. You observe how it responds, and you fix what you find. You do this proactively, on your own schedule, before a real outage finds the same weakness for you. AI-powered self-healing is the reactive counterpart. When failures happen in production, and they always will, regardless of how thorough your chaos program is, the self-healing layer detects those failures in real time, reasons about their probable root cause, and takes autonomous remediation action, faster than any on-call engineer can. The best engineering organizations do both. They use chaos engineering to make the system more resilient. They use AI-driven observability to make it self-repairing when residual failures still get through. Here is the analogy I find most useful. Chaos engineering is your immune system's training program. Controlled, deliberate exposure to threats, so your system builds the equivalent of antibodies against specific failure modes. AI-powered self-healing is your immune system fighting an active infection in real time. Now, let me explain the specific AI techniques that make both capabilities possible. The first technique is anomaly detection. Traditional monitoring is threshold-based. You set a rule that says if CPU exceeds 85% for more than 5 minutes, then fire an alert. The problem with threshold-based monitoring is that every threshold has to be manually configured in advance by a human engineer. And thresholds calibrated for normal traffic produce false positives during legitimate spikes like a product launch or a viral marketing event. AI-powered anomaly detection trains on historical metric patterns for each specific service. It learns what normal looks like at every time of day, every day of the week, every point in the deployment calendar. When a metric deviates from the learned normal pattern in a way that statistical models flag as anomalous, the system fires. No manually tuned thresholds. No false positives from a Black Friday traffic spike that the model already knows is expected and seasonal. The second technique is automated root cause analysis. When an anomaly is detected, the system does not just report that something is wrong. It traces the causal chain through your distributed system, correlating anomalous signals across multiple services and infrastructure layers to identify the most probable origin of the fault. The third technique is autonomous remediation. Once root cause is identified with sufficient confidence, the system executes a remediation action from a predefined playbook. No human required. The self-healing loop architecture. Let me walk you through the 4-layer architecture of a production-grade, self-healing Kubernetes system, layer by layer. Layer 1 is the observability layer. Prometheus is the industry standard for Kubernetes metrics collection. Every pod, every node, every Kubernetes component exposes a metrics endpoint. Prometheus scrapes these endpoints on a configurable interval, typically every 15 seconds, and stores every data point in a time series database. The metrics Prometheus collects are the raw signals your AI layer reasons about: pod restart counts, container memory utilization, CPU throttling rates, HTTP error rates per endpoint, Kafka consumer group lag per partition, database connection, pool saturation. Every number describing the current health of your system feeds into this layer. For distributed tracing, which gives you request-level visibility as a single user request propagates through multiple microservices, you add Jaeger or Grafana Tempo alongside Prometheus. Traces are essential for root cause analysis because they let you follow one request across 15 service hops and identify exactly where in that chain a latency spike or an error was introduced. How AI observability works under the hood? Traditional observability is metrics, logs, and traces. You collect signals from your system, display them on dashboards, set threshold alerts, and wait for an engineer to notice something wrong. This model has 3 fundamental limitations, and I want to name each one precisely because understanding them explains exactly why the AI approach is different. The first limitation is that threshold-based alerting is blind to complex correlated failures. You set an alert for CPU above 85%. Fine. But what if the failure pattern is a gradual memory leak that never crosses any single threshold, yet creates a cascade across 5 services over 45 minutes? No individual metric crosses the alert line. The system is failing in slow motion, and your monitoring shows green the entire time. The second limitation is correlation at scale. When a distributed system has a problem, you might see 150 alerts fire simultaneously across 30 different services. The root cause is one thing. The symptom cloud is enormous. A human engineer has to mentally trace back through those 150 alerts at 2 a.m. under pressure to find the single event that started it. Research from the Gremlin reliability team puts the average manual correlation time at 22 minutes. And that is for experienced engineers who know the system well. The third limitation is an irreducible latency floor for human response. Even with perfect monitoring and excellent runbooks, you still need a human to wake up, log in, read the context, make a decision, and execute a remediation. The floor for a skilled SRE team under ideal conditions is somewhere between 5 and 15 minutes. In practice, it is always longer. AI-driven observability attacks all three limitations at once. Here is the architecture that makes it work. The foundation is OpenTelemetry. If you are not already familiar with it, OpenTelemetry is the open-source observability standard that has become the undisputed industry default for distributed system instrumentation. Every service in your platform emits three types of telemetry through OpenTelemetry. Metrics, which are numeric measurements over time, like CPU, utilization, request rate, and error rate. Traces, which are end-to-end records of individual requests flowing across multiple services. And structured logs, which are machine-readable event records from each service process. All three signal types flow into a centralized observability backend. This is where the AI layer begins its work.
The first thing the AI does is anomaly detection through unsupervised machine learning. Instead of checking whether a metric crossed a static threshold, the AI model builds a dynamic baseline for every metric in the system. It learns what normal looks like for each service at each hour, each day of the week. Traffic patterns on a Tuesday morning look fundamentally different from Saturday night. The model knows this. When a metric deviates from its expected dynamic baseline by a statistically significant margin, the engine flags an anomaly. This catches failure signatures that threshold-based alerting cannot see at all. The second thing the AI does is automated causal correlation. When multiple anomalies appear across different services within a short time window, the engine uses causal inference to identify which anomaly caused the others. It analyzes timestamps and the known dependency graph of the system. Service A's anomaly appeared 8 seconds before Service B's. Service A makes synchronous calls to Service B in the normal request path. Causal inference concludes with high confidence that Service A is the probable root cause, and Service B is a downstream symptom. That correlation work that took a human engineer 22 minutes now happens in under 3 seconds. The third thing the AI does is autonomous remediation. Based on the identified root cause, the engine matches the failure pattern against a library of known remediation playbooks and executes the appropriate response without waiting for human approval. We will look at exactly what that execution looks like in the next section. The self-healing loop, second by second. Let me walk through the self-healing loop second by second so you can see exactly what is happening technically inside that 54-second resolution window from the opening. Second 0. The checkout service pod consumes beyond its memory limit and is killed by Kubernetes. Kubernetes immediately restarts it. Normal behavior. The pod enters CrashLoopBackOff because the memory leak causing the kill is still present in the application code. Every restart triggers another kill. Second 11. The AI observability engine detects 3 simultaneous anomalies. Memory consumption for the checkout deployment spiked sharply in the 90 seconds before the kill event. The pod restart count for the checkout deployment has crossed the anomaly threshold. And the open database connection count for the checkout service is declining at a rate that is inconsistent with the traffic volume. Connections are being abandoned, not properly released.
The engine immediately queries the audit event log for recent changes to the checkout service. It finds a deployment of version 2.4.1 that completed 7 minutes ago. It runs a Pearson correlation between the memory growth timeline and the deployment timestamp. Confidence score that the deployment is the root cause is 94%. Second 19. The causal inference engine traces the downstream effects. The abandoned database connections are exhausting the database proxy connection pool. The proxy is now returning connection errors to the session management service. The session management service is not failing. It is queuing requests it cannot process. The queue depth is growing at 340 requests per minute. If the queue continues growing at this rate, the session management service will exhaust its own memory within approximately 4 minutes. The engine updates the severity assessment. This is not a single service incident. This is an active cascade. Remediation priority escalates to immediate. Second 23. The remediation engine selects the rollback and flush playbook. It sends a rollback instruction to the GitOps controller to redeploy the checkout service at version 2.4.0. Simultaneously, it calls the database proxy management API to forcibly release all open connections associated with pods running version 2.4.1. Both operations are dispatched in parallel. Second 38. The rollback is in progress. Version 2.4.0 pods are initializing. Readiness probes are not yet passing. The forced connection release has cleared the database proxy. Session management service begins draining its accumulated queue. Second 54. All checkout pods running version 2.4.0. Readiness probes passing, error rate returning to baseline, queue depth in session management service back to 0. The AI engine publishes a structured remediation report to the incident management system. The on-call engineer receives a Slack notification that says, automated remediation complete. Checkout service restored to 2.4.0. Root cause identified as memory regression. In 2.4.1, no action required. That engineer never woke up. Now, I want to say something that I think gets lost in a lot of vendor marketing around this technology. Autonomous remediation works reliably when the failure pattern is well understood and the remediation action is deterministic. Rollbacks, pod restarts, connection pool flushes, horizontal scaling, these are safe, reversible, well-bounded actions that the AI engine can execute with confidence. Where these systems still fall short is novel failure modes. A failure pattern that has never occurred in your system before has no match in the remediation library. Current AI engines handle this correctly by escalating to a human engineer rather than guessing at a fix. And that is the right design. You do not want autonomous systems taking aggressive action against situations they do not understand. The practical reality for most teams today is a hybrid model. Known patterns resolved autonomously, novel situations escalated to humans with a rich AI-generated diagnostic summary that cuts manual correlation time by 80 to 90%. Chaos engineering, why you break your own system on purpose. Here is a question that sounds completely backwards when you first hear it. If AI observability can detect and fix failures automatically, why would you ever intentionally break your own production system? The answer is straightforward once you think it through. Your AI system can only recognize and fix failures it has seen before. Its remediation library is only as rich as the failure history of your platform. If certain failure modes have never occurred in production, they do not exist in the AI's pattern recognition model, which means when they do eventually happen in production, they happen at the worst possible time without any autonomous response capability. Chaos engineering solves this problem by generating controlled, intentional failure data before those failures happen organically. Netflix built the discipline in 2010 with a tool called Chaos Monkey. The premise was simple and aggressive. Chaos Monkey randomly terminates virtual machine instances inside Netflix's AWS production environment, not in staging, not in a test cluster, in production, with real users actively streaming content. The logic is counterintuitive, but rock solid. If your system cannot survive the loss of a single virtual machine during business hours in controlled conditions, it absolutely will not survive the same failure at 2 a.m. on New Year's Eve when your engineering team is scattered and your traffic is 10x normal. You want to discover that gap on a Tuesday afternoon when your full team is available and the blast radius is manageable. Netflix evolved Chaos Monkey into an entire ecosystem of chaos tools they called the Simian Army. Chaos Kong terminates entire AWS availability zones at once. Latency Monkey injects artificial network delays between services. Conformity Monkey checks whether instances comply with best practice configurations. Each tool targets a different class of failure. But here is where modern chaos engineering diverges significantly from what Netflix built in 2010. Chaos Monkey operated randomly. It injected failures without knowledge of the system's current state. This produced valuable data, but also unpredictable blast radius. You might terminate the only running instance of a critical singleton service. Or you might inject a failure during a period when the system was already degraded, compounding a real incident with an artificial one. Modern AI-augmented chaos platforms like Gremlin and Litmus Chaos use what practitioners call steady-state hypothesis validation. Before any experiment runs, you define the expected healthy state of your system. P99 response, latency, under 200 milliseconds. Error rate below 0.1%. Memory utilization between 40 and 60%. These are your hypotheses about what normal looks like. The chaos experiment injects a controlled failure. The platform continuously validates whether the system maintains its steady-state hypotheses throughout. If it does, the system has proven its resilience to that failure type. If the hypotheses are violated, the experiment immediately aborts. The injected failure is reversed, and the platform records exactly what happened and where the resilience gap is. This is not random destruction. It is structured scientific experimentation applied to production infrastructure. The closed feedback loop, chaos meets AI observability. Now let me show you where chaos engineering and AI observability combine into something more powerful than either one is on its own. Traditional chaos engineering workflow. A chaos engineer designs an experiment, runs it manually, observes results manually, writes up findings, creates remediation tickets. An engineer implements the fix, and then reruns the experiment to validate the fix. That full cycle takes days or weeks. The AI-augmented version closes that loop in hours. Here's how it works on a Kubernetes platform using Litmus Chaos for experiment execution and an AI observability layer running alongside it. You define your chaos experiments as code. Each experiment is a YAML manifest living in your GitOps repository alongside your application infrastructure manifests. It declares the target resource, the failure type, the blast radius constraints, the steady-state hypotheses, and the automatic rollback conditions. This is infrastructure as code applied to chaos engineering. When the experiment runs, it notifies the AI observability layer to activate enhanced monitoring mode for all services in the experiment blast radius. The AI engine is now watching with full attention, sampling telemetry at higher frequency and building a real-time causal graph of how the injected failure propagates through the system. When the experiment ends, the AI engine produces 3 outputs automatically. The first is the causal failure map, a precise, time-stamped visualization of exactly how the injected failure propagated through the system, which services were affected, in what sequence, what the latency was between the initial failure and each downstream effect. This becomes training data for the AI engine's anomaly detection model, teaching it what this failure pattern looks like in the wild. The second is the drafted remediation playbook. Based on what it observed, the AI engine writes a proposed autonomous remediation procedure. If this exact failure pattern appears in production, here is the precise sequence of actions I would take to resolve it. The engineering team reviews and approves this playbook before it goes into the autonomous response library. The AI proposes. Humans validate. Autonomous execution happens only after approval. The third is the resilience gap report. If any steady-state hypothesis was violated during the experiment, the engine identifies the specific architectural weaknesses that allowed it. No circuit breaker protecting service X from downstream latency. Service-wise resource limits are set too low for realistic traffic spikes. These become ranked engineering tasks, sorted by potential production impact. The loop is complete. Chaos experiments teach the AI new failure patterns. The AI builds autonomous remediation playbooks from what it learns. Those playbooks protect the system in production. New chaos experiments continuously expand the coverage of known remediable failures. The engineering team stops fighting fires and starts designing the fire suppression system. How Netflix, LinkedIn, Amazon, and Google actually do this. Let me give you specifics from the 4 organizations that have been running AI-augmented reliability engineering at production scale long enough to have real data. Netflix operates a system they call CHAP, Chaos Automation Platform. The key architectural decision Netflix made with CHAP is borrowed from A/B testing methodology. When a chaos experiment runs, Netflix splits a small slice of real production traffic into 2 groups. The control group gets normal conditions. The treatment group gets the injected failure. CHAP monitors both groups simultaneously and measures the user experience delta between them in real time. If the failure causes statistically significant degradation in the treatment group, the experiment aborts immediately, and the rollback executes automatically. This approach means Netflix can run chaos experiments continuously in production without meaningful risk to the user experience. The sample size is small enough that the business impact is negligible. The engineering signal is rich because it is real production traffic, not synthetic load. LinkedIn runs a chaos framework called SimoOrg. What is distinctive about LinkedIn's approach is how they prioritize experiments. Rather than targeting failure types randomly, Siebel.org analyzes LinkedIn's full incident history and identifies which failure modes have historically been most disruptive in terms of mean time to resolve and actual user impact. It then designs chaos experiments that target those patterns first. They are systematically building resilience against the exact failures that have already hurt them the most. Amazon's game day culture is legendary inside the company, even if it is less publicly documented than Netflix's tooling. Amazon teams regularly run full-scale simulated failures, where an entire service is intentionally taken offline. The team observes how the rest of the system degrades and documents every resilience gap that surfaces. What Amazon has added more recently is AI-generated incident timelines during game days. Instead of engineers manually correlating what happened, the AI observability layer produces a structured narrative of the incident automatically, within minutes of the game day ending. Engineers can focus the debrief on solutions rather than spending an hour just reconstructing what happened and in what order. Google's equivalent practice is called DIRT, Disaster Recovery Testing. DIRT exercises are organization-wide. Teams lose access to internal tools. Services are taken offline. Network partitions are simulated. The scope is deliberately uncomfortable, which is the point. Google's AI observability tooling generates real-time readiness dashboards during DIRT exercises, showing which services are responding as expected to chaos and which are surfacing unexpected gaps. The pattern across all four organizations is identical. Chaos engineering is not a quarterly event or an annual audit. It is a continuous, automated, data-driven engineering discipline. And the AI observability layer is what makes continuous chaos engineering operationally sustainable at scale. How to start implementing this today? Let me give you a realistic implementation path for a Kubernetes-based platform, not a vendor pitch, a practical engineering progression. The first thing you need before any chaos experiment is complete observability coverage. Every service instrumented with OpenTelemetry, every pod emitting structured logs, distributed tracing operational across service boundaries. If you cannot answer arbitrary questions about your system's behavior under normal conditions from existing telemetry, you will not be able to interpret anything a chaos experiment produces. For most teams, this takes 2 to 4 weeks, depending on how many services need instrumentation and how many were built without observability in mind. Once your telemetry foundation is solid, deploy your AI observability backend and let it run in monitoring-only mode for 2 to 4 weeks before you run a single chaos experiment. Dynatrace Davis, Datadog Watchdog, and AWS DevOps Guru are the 3 most mature production-ready options as of early 2026. The AI engine needs that observation window to build accurate dynamic baselines for each service. Skip this step, and your anomaly detection will be noisy enough that engineers stop trusting it. When you graduate to chaos experiments, start in a staging environment that mirrors production traffic patterns as closely as possible. Single pod, CPU, stress injection. Network latency between 2 well-understood services. Single pod kill for a service running multiple replicas. At this stage, you are not looking to break things. You are validating that your AI observability layer correctly detects and correlates the anomalies you are intentionally producing. Build confidence in the detection before you build confidence in the remediation. From there, you move to production experiments with strict blast radius constraints. Use steady-state hypotheses. Define abort conditions explicitly before each experiment runs. Start with services that have strong redundancy and well-understood fallback behavior. The final stage is automated continuous chaos. Once you have a validated experiment library and your AI engine has demonstrated reliable detection and remediation for known patterns, automate the experiment schedule. Run rotating experiments during low-traffic windows. Review weekly diagnostic reports rather than individual incidents. Your on-call rotation shifts from firefighting to architecture review. Most engineering teams reach the controlled production experiment stage within 3 months of starting this work. Fully automated continuous chaos with AI-driven remediation is typically a 6 to 12-month journey for a platform running 20 to 50 services. 4 things worth taking with you. The first thing is the distinction between observability and monitoring and why it matters practically. Monitoring tells you when a threshold was crossed. Observability lets you understand why the system behaved the way it did. The test is simple. If you can answer any question about your system's behavior from existing telemetry without deploying new instrumentation, your observability is solid. If investigating an incident requires adding a new metric or log field, you have an observability gap. Fill those gaps before you worry about chaos experiments. The second thing is that chaos experiments reveal false assumptions, not just infrastructure failures. Every time you run an experiment and the system fails in an unexpected way, what you have really discovered is an assumption your team held about how the system works that turns out to be wrong. The goal of chaos engineering is not to eliminate all failure from your platform. That is not achievable. The goal is to replace false assumptions with verified facts before those assumptions cause production incidents at the worst possible moment. The third thing is that autonomous remediation requires documented boundaries. You need to define in writing which actions your AI engine is authorized to take without human approval. Rollbacks, pod restarts, connection resets, horizontal scaling, these are generally safe autonomous actions because they are reversible and bounded. Database schema changes, cross-region traffic rerouting, and service decommissioning are not autonomous actions because they are irreversible or have large, unpredictable blast radius. That boundary should be reviewed by the engineering team every quarter as the system evolves. The fourth thing is that blast radius estimation is not optional. Every chaos experiment should come with a documented worst-case impact estimate before it runs. How many users could be affected if this experiment reveals a real gap that is larger than expected? What is the maximum degradation this experiment can cause given the blast radius constraints you have set? If you cannot answer those two questions before the experiment runs, the experiment is not ready to run. Let me bring it together. Traditional SRE keeps your systems reliable through excellent human engineering and disciplined process. AI-driven observability takes that foundation and adds machine speed anomaly detection, automated root cause correlation, and autonomous remediation for known failure patterns. Chaos engineering continuously expands the library of known patterns by injecting controlled failures and teaching the AI system what each failure mode looks like before it happens in production, organically. Together, these three capabilities form a reliability loop that gets smarter over time. Chaos engineering generates the training data. The AI engine handles known failures without waking anyone up. Your engineering team focuses on novel problems, architectural improvements, and building the next generation of the platform, instead of triaging alert storms at 2 a.m. Netflix, LinkedIn, Amazon, and Google are not running this model because it sounds interesting in an architecture review. They are running it because at their scale of complexity, there is no alternative that actually works. Subscribe right now because the next video in this series covers AI-powered performance testing. Specifically, how to use production traffic analysis to generate realistic load test scenarios automatically instead of handwriting them from assumptions that are always out of date. And I genuinely want to hear from you in the comments. What is your biggest Kubernetes reliability challenge right now? Alert fatigue? Slow incident correlation? Testing changes in production safely? Slow mean time to resolve?